Hello everyone, welcome back. This is Mr. Hossein Wasabi, and in this video we'll be quickly looking at some of the questions that I sent in the group for those that are part of the group. And if you're not part of the group, you can use this video as a way of revising what I was teaching. Alright, so before we begin, do not forget to like and subscribe to the channel. Alright, let's get to it. So the question reads that the diagram below shows a transformer that operates a lamp rated 12 volts, 3 amps. So as you can see, you have the transformer here. You have the 240 main supply. This is the primary core, as we all know. This is a soft iron core, and this is the secondary core, and this is the output voltage and the output current. Now I've been told that if the transformer has 240 volts as supply and it is 100% efficient, now what current will flow in the supply? It's a very good question. I know most of you by first glance you might not get it right, but with a little bit of more practice you get a hang of it. So now, just a quick reminder, every time you hear that it's 100% efficient, be mindful that what we're looking at is what we call an ideal transformer. An ideal transformer is simply just a transformer that is 100% efficient. So when a transformer is 100% efficient, it means that the power input is equivalent to the power output. This means that if you look at the formula for power is literally the rate of doing work. But in simplicity, power is a product of current and voltage. So if we understand that power is current times voltage, then the power input, which is current times voltage, will be equivalent to the power output, which will be equivalent to current times voltage. Now one thing you should understand is that the power input is on the primary core. So this will be the current in the primary times the voltage in the primary, being equivalent to the current in the secondary times the voltage in the secondary. If we had to pick out data and see clearly what we need, if you look at the current in the primary, you don't really have it because that is the current that will flow in the supply. So current in the primary, there is no. The voltage in the primary, as you can see, is being supplied with 240 volts. And the current in the secondary is about 3 amps. And the voltage in the secondary, as you can see, it's given to be 12 volts. So now with this information, we can use this formula and find our value. So we know current in the primary times the voltage in the primary is equal to the current in the secondary times the voltage in the secondary. So now let's make the current in the primary, since it's the one we're looking for, the subject of formula. By doing so, we divide both sides by the voltage in the primary, and then the other side by the voltage in the primary. And you have the current in the primary being equal to the current in the secondary times the voltage in the secondary over the voltage in the primary. So current in the primary is equal to, now what is our current in the secondary? The current in the secondary is 3 amps. The voltage in the secondary is about 12. And the voltage in the primary is 240 volts. So if you compute this, you end up having something that will give you 36 on top. So you have 36 divided by 240. And since calculators are allowed, if we divide this, 36 divided by 40, if you reduce, you end up having something like 3 over 20, but we want them in decimal fractions. So it's going to be 0.15. It's going to be 0.15 amps. So this will be the current that will flow in our supply. And this is how you go about solving the first question. So let's move on to the second question. Now the second question says that you have a figure that represents a transformer with a primary core of 400 turns and a secondary core of 200 turns. You've been given a label, the diagram. So you have primary, secondary, a resistor which resists the flow of current, and the soft iron core. So if you look at this transformer, you find that the number of turns in the primary is more than that in the secondary. And yes, we can deduce from that okay, this transformer is really a step down transformer because it has more voltage in the primary as compared to the secondary. So it's stepping down the amount of voltage. So question A says the primary core is connected to 240 AC mains. You get the secondary voltage. So here we haven't been told that this is actually an ideal transformer. It's just a regular transformer. So which means that efficiency is not really 100% because some energy is lost to the friction. So let's try and collect data and see what we have. So the number of turns in the primary being equivalent to 400, the number of turns in the secondary being equivalent to 200. Then we also have the voltage in the primary, which is about 240 volts. But we don't really have the voltage in the secondary, because that's the question. It's saying calculate the secondary voltage. That's what we're looking for. So now here what we have to do is to use the turns ratio, because there are literally like about two formulas you need to know under transformers, like the turns ratio and the ideal transformer formula, where you know that power input is going to the power output. So if I use the turns ratio, I know that the number of turns is equivalent to the amount of voltage. That's why I said that if you look at the primary core, we have more turns than the secondary core. And since we have more turns, we have more voltage here as compared to that. So that is where the turns ratio comes in. So this means that if the number of turns is equivalent to voltage, then the number of turns in the secondary is over the number of turns in the primary, being equivalent to the voltage in the secondary over the voltage in the primary. So what we can do here, since we're looking for the voltage in the secondary, we can try and make the voltage in the secondary the subject of the formula by just cross multiplying. Don't ever do that. That means you've cancelled the question. Just cross multiply in your head. So you're going to have voltage in the secondary times the number of turns in the primary being equal to the number of turns in the secondary times the voltage in the primary. Then since I want to make Vs the subject of the formula, I divide both sides by what? Np. Even the other side, Np. That cancels with that. So the voltage in the secondary is equivalent to the number of turns in the secondary times the voltage in the primary over the number of turns in the primary. So the voltage in the secondary will be the number of turns in the secondary, which is about like 200, as you can see from the data, times the voltage in the primary, which is like 240, divided by the number of turns in the primary, which is about 400. So if we simplify furthermore, the voltage in the secondary will be equivalent to, if you compute this, you end up having about 120 volts. So this is the amount of voltage that you have in the secondary coil. So now, if you look at B is quite different. B says, explain carefully how a transformer works. So now, be mindful of this. I hope you will see my handwriting. It's going to be a bit difficult, but I hope you can bear with me. So the working principle of a transformer is that, firstly, the EMF is supplied. So the EMF is supplied to the primary core. So now, once the EMF is applied to the primary core, what happens? That current will do what? Will flow. Okay? Now, when the current flows, it creates a changing magnetic field. This is the first point you need to know. When the EMF is applied to the primary core, current flows, creating a changing magnetic field. That's the first point. Now what happens is that the changing magnetic field is linked to the secondary core via the soft iron core, thereby creating an induced EMF in the secondary core, which is the voltage. So let me write that. So the changing magnetic field, is linked to the secondary core via the soft iron core, and when that happens, that's what you conclude by saying thereby creating an induced EMF. In the secondary core. Alright, so now, in a nutshell, EMF is supplied to the primary core, current flows, creating a changing magnetic field. Then the changing magnetic field is linked to the secondary core by the soft iron core, thereby creating an induced EMF in the secondary core. Like I said, EMF is the voltage, in simple terms. Now, if you look at C says, why is soft iron used for the core instead of steel? So why iron? Why not steel? So these are the reasons. The first reason, which is mostly common, is that it loses less energy. Then the other one, I'll just give two, is that it's a soft magnetic material. But there are more reasons that I gave in the video. Alright, so the last one says if the current in the primary core is 3 amps, calculate the current in the secondary core of the transformer, assuming that the current is 100% what? Efficient. So for this work, I'll do it on the other part of the screen. But remember what we have. So in that question, what we have is as follows. From the data, we're given the current in the primary being equivalent to 3 amps. We're also given the voltage in the primary being equal to 240 volts. The voltage in the secondary, which we found to be what? 120 what? Volts. And we need the current in the what? Secondary. Because I've been told to say that we need to assume the transformer is 100% what? Efficient. So this means that the power input is equal to the power output. So this means that the current in the primary times the voltage in the primary is equal to the current in the secondary times the voltage in the what? Secondary. So we need to make the current in the secondary the subject of the formula. So that's divided by the voltage in the secondary this side, even the other side would be the same. So the current in the secondary is equal to the current in the primary times the voltage in the primary over the voltage in the what? Secondary. So the current in the secondary is equal to what we have as 3 as the current in the primary, as well as the voltage in the primary being equal to 240 divided by the voltage in the secondary, which we found to be 120. If you compute this, you get your current in your secondary to be equivalent to 6 amps. And this concludes the questions that we are looking at in this video. Alright, so if you have questions, please you can always ask me by reaching me out on WhatsApp on this number attached to the screen. The number I'll put in my description. Alright, my name is Mr. Hussein Mwasapi. Remember to like and subscribe to the channel, and don't forget to strategize before you become a statistic, unless you want to push for that distinction.